So orbital box diagrams. Orbital box diagrams are basically a visual representation of electron configuration. So basically what this means is that you take your electron configuration and turn it into some picture format or diagram. Now, before I start off with examples to explain this concept, I want to explain 3 rules that you must keep in mind while drawing your orbital box diagrams. The first rule is the Hunds rule. The Hunds rule basically states that every orbital in a subshell is singly occupied with 1 electron before any orbital is doubly occupied, and all electrons in singly occupied orbitals must have the same spin. So basically what this means is that when you're filling up your sublevel of your p orbital, d or f orbital, you must fill up the orbital with 1 electron first before you fill it up with the second electron. I know this may sound confusing right now, but when we do examples I will further clarify this topic. The next 2 principles I want you guys to keep in mind is your off-bell principle and your Pauli exclusion principle. I know you guys must have learned these principles already in the previous videos, but just to clarify them, because you will need to know them very well in order to draw your orbital box diagrams correctly. So your off-bell principle basically states that electrons fill orbitals starting at the lowest energy level and they build themselves up to higher energy levels. And your Pauli exclusion principle states that an orbital can only hold up to a maximum of 2 electrons, and those electrons must have an opposite spin. Now, for your off-bell principle, one thing I want you guys to do to make this whole concept much easier is to draw this little chart out. This little chart basically helps you determine which energy level comes after which one, which can sometimes be a bit confusing. So as you can see here, it shows you that the 1s energy levels comes first, and then it's the 2s, and then 2p, 3s, 3p, 4s, and going on forward. So when you're drawing your orbital box diagrams, I suggest you guys draw this chart first so you can use it as a reference to see which energy level comes next. Okay, so let's just leave this on the side here. Okay, starting off with a simple example, hydrogen. So after looking at your periodic table, you know hydrogen only has 1 electron. So what you want to do to start off with is draw your box, which represents your orbital, and then draw 1 arrow facing upwards, which represents your 1 electron. And since hydrogen only has 1 electron, this is all you need to do. Now remember, when you're drawing your first arrow in your orbital, it must always be pointing up, and your electron represents 1 arrow. So to clarify what I just said is your arrows represent your electrons and you use a box to represent your orbitals. Now when you have an orbital with more than 1 electron, so a maximum of 2 electrons, they must have the opposite spin. So what this means is that 1 arrow must be pointing up and 1 arrow must be pointing down. Pretty simple. Okay, so moving on to our next example, which is helium. Now helium, we know, has 2 electrons, so we know that we're gonna have to be drawing 2 arrows. So you draw your first arrow, as I said, you draw it pointing up, and now since you have a second arrow and it must have an opposite spin, you must draw the arrow pointing down. It's pretty straightforward. That's all you have to do. So remember, you have to draw your box to start off with, and then you draw your arrows according to how many electrons you have. Okay, so let's try another example. Lithium. So we know lithium has 3 electrons after looking at your periodic table. So we know that its electron configuration is going to be 1s squared and 2s1. So same process. You start off by drawing 1 arrow up, 1 arrow down. So now you have satisfied 2 electrons. You have 1 electron left, so you're going to move on to the next energy level and draw 1 arrow pointing up. Now one thing I want you guys to remember is that whenever you're doing your orbital box diagrams, you must label your energy level under the box. So you know this one is your 1s sublevel and this is your 2s sublevel. And once again, you can use this chart to help you remember that. So you know your 1s comes first and then your 2s comes next. moving on to another example, a little bit harder one, boron. So after looking at your periodic table, you know boron has 5 electrons. So the electron configuration is going to be 1s squared, 2s2, and 2p1. 5 electrons in total. So you start off by doing the same process. One arrow pointing up, one arrow pointing down. That's 2 electrons in total. One arrow pointing up, one arrow pointing down. Now you have 4 electrons. You have one more electron left, so you're going to have to move to the next energy level, which is your p orbital. So you're just going to draw one arrow pointing up. Now remember, you must label your energy levels under the boxes. So this is the 1s, 2s, and this whole thing is a 2p. Pretty straightforward. Now, for the next example, neon, I want you guys to pay attention very close because this is where it gets a little bit confusing. Neon, we know, has 10 electrons. So your electron configuration is going to be 1s2, 2s2, and 2p6. Notice how your p orbital is going to be full in this example. So I want you guys to pay attention to how I fill this orbital out. So you start off with the same process. One arrow up, one arrow down. Now you have 2 electrons. One arrow up, one arrow down. 4 electrons. Now, when you're filling your p orbital out, you must follow the Hunds rule I stated, which basically states that you must fill each orbital up with 1 electron before you fill it up with a second electron. So this is how you fill it up. You fill it up with 1, and then you move on to the next orbital. You don't draw your usual arrow pointing down. So you do 2, and then you do 3. Now that you have satisfied the Hunds rule, you can now draw a second arrow or electron into the orbital. So you can draw 4, 5, 6. So that is the correct way to fill out your p orbital. Okay, so now you have to label your energy levels. So 1s, 2s, and 2p. Okay, so one last thing about this example I wanted to point out is that, let's say on a test or exam, your teacher asks you to find the magnetic spin for the 9th electron. So the way you want to count is that you want to count like this. You want to count 1, 2, 3, 4. Now pay attention carefully. You want to count 5, 6, 7, 8, 9. So this is your 9th electron right here. Notice how I didn't go 5, 6, 7. I went 5, 6, and 7. So that's the correct way to count. You count according to your Hunds rule. Okay. Okay. So now I just want to do one more example, and then we'll talk about one more short topic and end the video off. So carbon, we know carbon has 6 electrons, so its electron configuration is going to be 1s2, 2s2, and 2p2. So you start off by doing the same process. One arrow up, one arrow down. That's 2 electrons. One arrow up, one arrow down. That's 4 electrons, and now you have 2 electrons left. So you do one arrow up and one arrow up. Remember, you have to follow the Hunds rule. Now last step is labeling your energy levels, so 2p. And that's basically the process. Okay, so now I just want to explain one short topic and then I'll end the video off. Okay, so this short topic is about half-filled S subshells. So basically, half-filled S subshells only occur through some transition metals such as copper. This is where these elements like to have an half-filled S subshell. So basically, instead of having a maximum of 2 electrons filled, they only have 1 and give that electron to the next energy level. These are some exceptions you guys have to know, and you can identify them by simply looking off your periodic table. So let's use copper as an example. So copper, we know, has 29 electrons. So the electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6. Now, pay attention closely. Instead of having a 4s2 subshell, it's gonna have a 4s1, and then it's gonna give the next subshell the electron. So 3d10. This is the correct way to write it. Now, some of you might write it like this: 4s2 and 3d9. This is the incorrect way, because copper is that one exception where it likes to have its subshell half filled. Its S subshell half filled. So to identify this, you just simply look at your periodic table and you leave your S subshell half filled, and then you move the electron to the next energy level.